So I'm really happy to be here. I was a 2016 Blue Waters graduate fellow, and today I'm going to be talking to you about something that was a continuation of my fellowship project through Blue Waters extension allocation, studying how we can manipulate small droplets in confined or like microchannel flows using complex fluids. And so I use Blue Waters in my work to engineer complex fluids and soft materials at the nanoscale. And so one thing I learned when giving talks to general audiences like this is to make sure that everyone really understands everything in your title before you get into the talk. And so that's where we're going to start, is talking a little bit about what the problem is that we're trying to solve. So in general, when I'm talking about manipulating particles in a microchannel, I have a schematic kind of like this in mind, where I have some sort of feed stream that contains particles in it. So those could be like hard particles that you want to filter out of something like water. Maybe they could be a droplet of oil. They could be a cell that you need to try to enrich into something that you can collect. And so when it's coming into the feed, we assume that everything is pretty well mixed. And then if I go far enough down this microchannel, which is something that's on the nanometer to micron scale in diameter, then ideally what I'd like to do is end up with something where everything is very well ordered. I've put everything in the place that I'd like it to be, and then I can do something like this here, where I have this psi-shaped channel where I collect the thing that I manipulated out of this thing, and I reject the rest out of the other sides. And so the idea of this is really strongly connected to the microfluidics community, and the idea of having like a lab on a chip where I could process fluids very quickly and for some sort of reconfigurable design. And some of the applications are ones that I've mentioned, like filtration, fractionation, where I might have mixtures of particles of different sizes and I want to pull a certain type out, cell sorting. This sort of manipulation of particles has relevance to oil recovery and wastewater treatment, where I might have a multiphase thing and I want to, like, say, pull oil out of the ground or pull oil out of water. But so this is really, a lot of efforts has been made over the last 10 years towards solving this problem, primarily experimentally. But a lot of the efforts towards that have been very ad hoc, where you can design a microfluidic device that works for the problem that you have at hand, the thing you want to separate, the fluid that you have. But it's a really important challenge to be able to systematically do that in a way that works generally and doesn't have to be particular to a given problem. And so one way that people, and especially our group, have been thinking about how to solve that problem is to turning towards this rich library of fluids, which are called complex fluids. So rather than try to manipulate or engineer necessarily the microfluidic device directly, we want to think about engineering the thing that goes through it. So maybe we could add something into the sample that we're trying to purify, and then that'll help us extract the thing that we care about. So complex fluids, there are tons of examples of them just in our everyday life. Things like consumer products like shampoo or detergents, shaving cream. Biologically, blood is a complex fluid. Paints, this is this weird cornstarch water mixture. You've probably seen like YouTube videos of people running on water. And so the signature of a complex fluid, as opposed to a simple or Newtonian fluid like water, is that the way the material behaves depends on the conditions that you're using it. So in the case of the cornstarch water mixture, if I press slowly on it, then it's a liquid, and I can go through it. But if I press really hard on it, then at those short time scales and short impulses, it behaves like a solid. And so a lot of these really unique properties come about from the fact that complex fluids are complex. They're mixtures of a solvent like water, but then you throw something else in it, like a macromolecule, a polymer surfactant. A polymer solution is a really classic example of this. So this is a model polymer chain. It's wiggling around right now at rest in a solvent in the background, and it's just going to kind of diffuse, and it samples the conformations, but then I turn a shear flow onto it. All of a sudden, the chain will stretch out. It snaps out. It goes under these tank treading-like behaviors. This is a predominantly microscopic phenomenon, but these microscopic behaviors translate up into the macro scale. So here I've plotted what's called the shear viscosity of the polymer solution. And so if I don't flow it very hard, then the viscosity is mostly constant. But if I start to flow it faster, then it does what's called shear thinning, and the viscosity actually drops down. So paint or ketchup are examples of fluids that do this. And so one cool thing about these polymer solutions is that they actually have a property that can help us solve our problem of manipulating droplets. So if I take a pinch of polymers and I throw them into this these particles that are in a microchannel flow, and I want to try to push all the particles down into the center line. So what happens is I put it under flow, the polymers deform like they did in the previous video, provided that I'm flowing fast enough, and then a very big, it turns out, is that the particles can move into the center. And this has been known for about 50 years for things that are millimeter size in diameter, pretty big, or even like tens of microns. This is this experiment. But a big question that we still needed to know is, we know this for large things. Not everything that holds true for large things, large in the sense of, I guess, this sort of problem, not necessarily the cosmology people here. But what happens when our particles become really small? And two effects happen. So one is that when we look at the nanoscale, we have what's called Brownian motion, which is thermal fluctuations, small kicks, small random forces that act on particles can cause things to wiggle around. Things are no longer deterministic. And so in the classical world, in the large scale world where things are big, if I had a tube and particles flowing, then they would tend to align around this ring if they were just in water. But if I have Brownian motion, then things tend to scatter around that ring, and it's an open question of, well, how well at the small scale is the thing actually on this ring, and how much of the time is it spending elsewhere? Another thing that happens is that when the particles get small, and if I'm in a complex fluid, like the polymer solution, well, polymers are macromolecular objects. They are maybe tens or hundreds of nanometers in size, and if I want to manipulate a nanometer-sized object, well, then now these things are actually pretty close in size to each other, and they can couple to each other incompletely. It's not like I have a really big thing moving through a continuous media anymore. It's a heterogeneous microscopic environment. And so what we thought was that, well, okay, at these small scales, well, you have average forces acting on particles. They're going to give the average direction of motion. And so things might, if the average forces are something like this, then they'll pinch out towards the side, like in this tube. And if you can get average forces that push you to the middle, then you'll go there. And then due to Brownian motion, you'll distribute somehow in this field, and then you can be a better or worse at manipulating the droplets. And so we're going to use simulations to test this because it's really hard to do a lot of these experiments at small scales because things like optical microscopy can be difficult with very small particles, and also you don't get information about, say, the complex fluid itself. You can only watch the thing that you can track. And so in order to do that, we're going to use mesoscale modeling techniques. So this is kind of the standard modeling chart of, like, so down here you have atomistic molecular dynamics type models, and even down here you have quantum. Then up here you have things like CFD and constitutive level modeling. So the problem with models down here is that they have too much resolution, that we can't bridge the length and timescales that we need to with the model, even on a system like Blue Waters. But if I go up to the continuum scale, then I smear out the fluctuations that I care about for these special types of complex fluids. And so I need to use what are called coarse-grained or mesoscale modeling techniques that bridge the span in between them. They include just enough detail to capture the problem I want, but not so much detail that it's computationally intractable. And so an example of the type of coarse-grained modeling we're using, this is from my chemistry kit. This is polyethylene, represented with atomistic beads. And when we think about turning this into a coarse-grained model, we might say, okay, so I have some spheres that are going to be connected together. Maybe they have a spring that represents a bond between them, and it can, that has a certain length based on the atomistic model. There's some sort of angle bending that sets this angle here. There's a dihedral twist that sets the orientation of them, and then there's also excluded volume interactions. So the models that we use are generally very simple, where we just think about these excluded volume things and the bonds to model flexible polymer chains. So a few years ago, we did one of these coarse-grained models where we had rigid particles, which are the spheres immersed in a polymer solution. And when we simulate it, initially everything's pretty randomly mixed, but over time, if you pay attention in the middle, you can start to see this enriched layer of red particles. They're focusing down here, and eventually we get a nice enriched region that we might be able to separate out. So those were rigid particles, so this is kind of confirming what people had thought, what happens at the macro scale does apply down to the micro scale, but there are fluctuations. And then the thing that we really wondered after having done this problem was, well, what happens if the things are droplets or cells that are deformable or squishy? And so to do that, this is where we came to Blue Waters. So we're going to use a technique called dissipative particle dynamics. So there we're thinking about like packets of fluid where one bead in our model typically represents like 3 to 5 water molecules kind of lumped together moving around in space. We can do the same thing for the droplet, so that's shown here in orange. We have polymer chains shown in green. We have walls up at the top and the bottom, and then we can tune the parameters that we care about to try to figure out what type of complex fluids will help us manipulate this drop better. What length should the polymers be? What concentration should they be? How fast do we need to try to flow this? And that's where Blue Waters was really key to enabling this research. We have, even with just considering those handful of factors, we have a fairly large parametric design space. So we tried 4 different polymer lengths, 3 polymer concentrations, and 5 flow rates. And just one of these simulations has about 400,000 DPD particles in it, which we run on the XK nodes on Blue Waters. We can use 4 of them efficiently, run a simulation in about 2 days using the Hundi Blue simulation package, which we modified for these types of simulations. And Blue Waters was really the only system available to us at the time that could get us this both level of throughput and GPU resources available at the same time. Okay, so what did we learn from doing that? So the first thing we learned is that a droplet in a neat solvent acts a little bit differently than a rigid particle. So this is now just a droplet where I didn't put any polymers in yet, and I'm just going to change how fast I flow the mixture. So if I had a rigid particle, what happens is usually that the particle will just end up pushing harder and harder out to the outside. In the case of the droplet, it actually tends to migrate a little bit inward. So we can get some cross-stream migration from just having a droplet in a microchannel flow, which is really useful. But here 0 is the middle of the channel where we would like to collect the particles, and 1 is the wall. So we see that the droplet is still on average spending a lot of its time far from the center, so that's not really great for us for collecting these droplets. So why does it do this? What is different in the droplet compared to the hard particle? The shape of a droplet depends on where it sits in a flow field. So we can characterize the shape of the droplet, and this is something where simulations are really useful. It's not something you can always get in experiments, is that we can, for particles this small, so we can characterize how stretched is it in one direction versus the other. And this is a function of the local capillary number. And so we see that down here is particles that are not very deformed. And generally across flow rates, all these different flow rates, we do see that the droplet is deforming in the flow, which is what you expect physically, and correlates very strongly with why a particle would want to migrate to relieve some of this deformation. The other thing that happens is that the droplet will change its alignment in the flow, again, related to relieving some of this stress with the flow. We then added some polymers into the mixture to try to see, okay, can we improve on the focusing behavior that we had originally without any polymers in there? So the first thing we did was characterize the flow field, and so that's what we're showing here is the velocity field between the 2 walls in the channel as we're adding different concentrations of polymer. This is a Newtonian solvent, and this is with a 10% weight polymer added to it. And so as we add more and more polymer, then we see that the peak velocity drops, which is consistent with a higher viscosity solutions, what you expect for a polymer solution. But also, these flow fields change their shape from being a parabola here to something more flattened in the middle, which is consistent with having a power law type fluid, which is a crude approximation of a shear thinning fluid that I described earlier in the talk. And so as we're doing this, we're making some changes to the flow field, but the thing that's most dramatic is what we do to the droplet. So out here, the blue curve is the distribution that I had on the other slide, where there is no polymer in it, it's just a Newtonian solvent, and the droplet is out here, away from the middle. And then as I add gradually more and more polymers, initially there's a little bit of a push outward, which we found was interesting and is, we think, a little bit of a weird polymer physics problem. But then as you add even more polymers, then eventually the droplet moves into the middle and focuses pretty strongly onto the center part, demonstrating that yes, even at the micro scale, we're able to manipulate droplets in this way. And we have varied some other parameters, but I think this is a good representation of what we learned from our simulations. So I hope that what I've been able to show you is how Polymer Solutions can be used to manipulate droplets in microchannels. We can use them to push the droplet into the middle where it might be recovered for some application. The droplet position and the shape depend sensitively on the details of the polymer solution and of the flow. So this gives us a nice engineering opportunity to control behavior and to design using only the fluid that's in the channel where the droplet or the particle is positioned. And so this is, we think, going to have important applications for processes like membrane filtration, where maybe you want to separate an organic from water, or for self-sorting, where you don't necessarily have a droplet, but you have some sort of squishy vesicle that you'd like to recover. And all the software that we developed in order to enable these simulations has been released open source on GitHub if anyone would like to try to do the same types of simulations. And so I'd like to thank first my collaborator for a lot of these projects, Arash Nico-Boschman from the University of Mainz in Germany. Also my postdoc advisor, Tom Truscott, for their help on this project. I'd like to thank the Blue Waters Fellowship for the allocation to work on this and the opportunity to continue doing that. And also to thank the Center for Materials for Water and Energy Systems at UT Austin, which is a DOE center studying water purification and filtration technologies. And with that, I'd like to thank you for your attention and be happy to take any questions.